Hello! Today I am going to talk about tunnel diode oscillators. Now, tunnel diode oscillators may seem rather strange, sort of like spooky action at a distance, which is something that Einstein didn't like. And when you read explanations about how tunnel diode oscillators work, you may find some hand waving or some things that are not fully explained or just don't make any sense. But if you thoroughly understand the fundamentals of electronics that we have already studied, if you understand Ohm's law, Kirchhoff's voltage law, how inductors act in DC circuits, and how tunnel diodes follow certain rules, the tunnel diode oscillators simply do what they have to do according to the laws and rules that electronics follow, that we've already thoroughly studied. So you really should make sure you thoroughly understand everything that we've studied up to now, understand your basic DC and AC electronics and how the components work. But let's go over some of the things we need to know just briefly before we get into tunnel diode oscillators so that we thoroughly understand what we are getting into. So let's start by Ohm's law, which is simply our voltage is equal to our current times our resistance. And I think we know that well enough that we don't need to go over any examples at this point, but let's take a look at Kirchhoff's voltage law before we move on. So Kirchhoff's voltage law states that the voltages in a series circuit must add up to zero. And I modify that in my explanation saying that we have a power source or a voltage source, which we'll just label as a battery, and we're going to have some consuming components, which we will just have resistors at this point here, and that the voltages across these resistors must add up to the source voltage. So let's say we have 15 volts here, plus to minus, and we'll call that a positive voltage. And when we have current flowing into our consumers, where the conventional current encounters an impedance, we're going to get a backup of voltage, and so we will get a positive increase in voltage there with a lower voltage on the other side. And of course, we get the same thing over here, positive to negative. And let's say that this is 10 ohms, and this is 5 ohms just for mathematical convenience. And so what do we have? We have a total of 15 ohms, total of 15 volts. So how much current is that? It's 1 amp of current. So we have 1 amp going through 10 ohms. How many volts are we going to get in this differential across there? We're going to get a total of 10 volts. So if we take a voltmeter and anchor our black probe right here, and then take our red probe and probe around the circuit, we will find that we have positive 15 volts here, and of course the same over here, positive 15 volts. And then we're going to have a higher voltage here and a lower voltage there, so we will lose voltage going across this resistor. How much? 10 volts. So we start with 15, we lose 10, we have positive 5 volts left over. And now we have 1 amp going through 5 ohms. We're going to get a higher voltage here and a lower voltage there. What's that difference going to be? Well, Ohm's law says that 1 amp through 5 ohms, that will be 5 volts. So let's draw that here, from there to there, 5 volts. Higher voltage, lower voltage. And so we start with 5, we lose 5, we end up with 0 volts here, which of course, if we go over to here, where we have the probes in the same place, we have 0 volts. So what does our voltmeter tell us? It tells us the difference between two voltages. If the two probes are at the same place, they are at the same voltage, there is no difference, so we read 0 volts. So there's a quick review of Kirchhoff's voltage law. But let's throw a shoe in the works here. What I'm going to do is, let's say we replace this resistor with a battery. Let's make that a 5-volt battery, and just for the fun of it, I'm going to have that polarity reversed. So this is positive to negative. So as we looked at that before, remember I said this was a positive voltage? Well, where we've reversed the voltage, notice it's positive here, negative to positive, positive to negative, it's reversed, so that's going to be a negative voltage. And so this is going to be another negative voltage, and let's make that 5 volts. So what's going to happen here? Well, we now have a total of 15 volts and 5 volts. Well, that's going to be like, well, let's see, we have a couple of batteries here. We've got to get our polarities right. Is that correct? Positive to negative, negative to positive, positive to negative, negative to positive, that's right. So that's going to be 15 volts. Well, if this was reversed, let's reverse it just for a second. We simply add them together, right? 15 plus 5 is a total of 20 volts. What happens if we reverse them? Let's see, got to get this drawn correctly. There we go. Well, now it's going to be 15 minus 5 volts, so it's going to be a total of 10 volts. So let's get that out of the way and see what we have around here. We have a total voltage between here and here of 10 volts, positive to, well, that's going to be our lowest voltage, so basically positive to negative. I'll leave the polarities here for now. So we have a total of 10 volts across, just for convenience, let's make this a 10 ohm resistor. So now we have a total of 10 volts between here and here. That 10 volts between, once again, between here and here. So that 10 volts is across that resistor, positive to negative. So 10 volts across 10 ohms means we have 1 amp of current. And if we look at our voltages across here, we start with 15 volts. Let's use our red pin here again. So if we start here at 0, we go up plus 15 volts. And at this point here, we will still have plus 15 volts. But now we have that 1 amp going through 10 ohms, so we are going to lose 10 volts here with plus 5 left over. And then what are we going to lose? 5 volts plus to minus and have 0 volts again. That doesn't mean anything because we're looking at that a different way, 0 volts. So if we have a voltage source here that's reversed in polarity, we're going to add the voltages together, which in this case is 15 volts and 5 volts, but notice they're opposing each other, so it's 15 minus 5, giving us a total of 10 left across that resistor, and we saw that we had a total of 1 amp, so we started with 15 volts, lost 10, lost 5, down to 0, and Kirchhoff's voltage law is satisfied. So now let's look at the next thing we need to review, and that is how an inductor acts in a DC circuit. I'm going to use the example circuit I used to explain how inductors react. So we're going to start with a voltage source and a resistor and an inductor. And I'm going to put a switch right here. And when I close that switch, I'm going to have a surge of current into this inductor. So what's going to happen? Well, that surge of current is going to cause a magnetic field to build, and as that magnetic field is building, it's going to induce a voltage, often called back EMF, inside the inductor that's going to push in the opposite direction. And so basically what I'm going to end up with at that moment in time is a battery that is pushing back in the opposite direction. So let's say this is a 10 volt battery. I'm going to end up with about 10 volts pushing the opposite way. So how much current am I going to have? I have 10 volts here plus 10 volts plus 10 volts here. So what's the voltage difference across this resistor? Well, remember that voltage is always a differential, and also 0 volts is not the absence of voltage. It simply tells us that two voltages are equal. So if I put my black probe here and my red probe there, they're going to each be at the same voltage. So the voltmeter is going to say I have 0 volts. So my voltage across that resistor is 0 volts. So I will have no current. Let's draw a graph over here real quickly. So I'm going to be at this point in the graph. This is time, and this is voltage across the inductor. So at this point I have my highest voltage. Let's do current in blue. And no current either, so I don't want to contaminate my blue pen, so I won't touch that. Now, as time goes by, what's going to happen is that magnetic field is going to slow down in this building. Now I know that it's not really getting bigger, but in electronics we say that because it's just easier to visualize. It's just getting stronger, but let's just say it's getting bigger, but it's getting bigger slower. So it's not creating as much of that back EMF. So that means the voltage after a certain amount of time, let's put our voltage in black, after a little bit of time, our voltage is going to come down a little bit. So there we are with our voltage over a certain amount of time. And because that voltage has gone down, so it's no longer 10 volts, remember this is an inductor, but I'm going to leave the battery there. Let's say it's dropped down to 8 volts, just kind of looking at what I have there. So now I have a difference of 2 volts here, so let's draw that correctly. Plus 10 plus 8. So I have higher voltage here, lower voltage there. Current's going to be flowing in that direction. I have 2 volts over, let's make it 1 ohm just for convenience, which is going to give us 2 amps of current flowing through the circuit at this point. So with my blue pen, I will show that our current has gone up to 2 amps at that point. And as time goes by, that magnetic field's still getting bigger, but it's slowing down. And so it's producing less back EMF, and this is going to eventually drop down to 0. And so we'll no longer have any voltage across there, 0 volts. And our current is going to be at its maximum current because that's basically a short circuit now. So let's just draw it as a short circuit. So our inductor is now a short circuit. And so we have our maximum current, so that's going to go up to whatever our maximum current is. And, well, 10 volts and 1 ohm, that's going to be, let's put the current in blue, 10 amps of current. So that's what's going to happen over time. Now, in my original demonstration, I put another resistor and switch over here for discharging the inductor, which I will now put back. So there's our inductor, and now we have 10 amps of current flowing through it. My magnetic field is fully built. I have a lot of energy stored in that magnetic field. In my original demonstration, I had another switch over here, so I could open that switch and close that switch. Well, let's just go ahead and do that, just for demonstration purposes here. So now I'm going to close that switch and open that switch. So what's going to happen? Now I have all this energy stored in this coil. And since I'm no longer pushing current into it, there's nothing to keep that magnetic field sustained. So it's going to start to collapse. So now it was building and causing a force pushing this direction, but now that it's collapsing, it's going to reverse direction of its force. And that current that wants to now stop because I've opened the switch. So I've opened the switch. There's nothing to push current through there anymore, so the current tries to stop. But the inductor is going to start pushing current in that direction. As we explained in the module on inductors, an inductor acts like a flywheel. It's hard to get current to go in, but once you get it going, it wants to keep going, and it's hard to stop. So that wants to keep that current going. And what's going to happen now, we now have, instead of a power consumer, we have a power producer. So when our current was being pushed in, we get a back voltage just like any other impedance. Where the conventional current goes in, we get a backup of voltage, so we get a higher voltage there and a lower voltage there. But when we stop that current, the magnetic field starts to collapse and it starts to push current in the same direction and wants to keep it going. Now this is a power producer, and power comes out of the positive side of a power producer, like a battery. The current is coming out of the positive side because it's producing power. Now this is producing power, so the current is coming out the positive side. So the polarity suddenly reverses. So on our graph here, this is going to be negative voltage below that line. So it's positive voltage down to 0. Now it's going to suddenly jump to negative voltage. So the graph here just simply says my voltage reversed. So now my voltage is down at negative voltage. What's it going to be? It depends on how fast that magnetic field collapses. And I can get voltages much higher than 10 volts. And now what's going to happen is that magnetic field is collapsing, and it first collapses very quickly, but it slows down. And I'm running out of graph over here, but we'll manage. So that voltage goes down over time. Down, it's going up. The absolute voltage, the value of the voltage is going down. So let's say it was 10 volts to begin with. Now it's gone down to, let's put it right about there, to 8 volts. But my polarity is reversed, so my voltage is going up compared to here. So it's a negative voltage. Remember what negative voltage is. It's not the opposite of positive voltage. It's just a voltage lower than some other voltage we have set as 0. So the voltage magnitude is decreasing, but it's going more and more positive. So the voltage is essentially going up towards 0. So there it goes. And as that magnetic field collapses more and more, that voltage goes closer and closer to 0. What's happening to the current? Well, the current was very high, but that current is now going down. And it's going to go down towards 0. And eventually we're going to reach the state that we were when everything started. Let's just erase all of our clutter around here. Clean that up. There's our open switch. There's our 10-volt battery. And we're eventually going to reach the point where this is completely discharged. There's no more energy in the inductor, no more current, no more voltage. And we're at this point here with 0 volts. So I put my voltmeter across here. Nothing, no voltage across either of them, no current. Only place I have voltage, of course, is still at that battery, which is disconnected from the circuit. So it went up and then it went down. But recall how in AC circuits I demonstrated how the impedance of an inductor, or the inductive reactance, increases as I increase frequency. Remember what I did? I imagined that I opened and closed these switches alternately to create alternating current across that inductor. Let's get rid of our polarity there. So that inductor started at a high voltage. I closed the switch. Let's just make those open switches now. I close the switch. I get my high voltage across the inductor, and that starts to come down. And at the same time, I get my 0 current through the inductor, which starts to go up. And then I flip the switches. So I open that switch and then I close this switch. And now everything starts to discharge. So my voltage jumps down to a negative voltage and starts to go down in magnitude, but up in relation to my probe here. So remember, my probe is at 0 volts. And what does my current do? My current simply goes back down to some lower current. Now I'm going to flip those switches again. Open that, close that. Now I have my current going through there, so my magnetic field reverses and starts pushing back again, and my voltage is suddenly going to jump back up to here and then start dropping back down. What's my current going to do? My current is going to start going back up again, and then I'm going to flip the switches again. So suddenly I stop the current, the magnetic field collapses, the voltage reverses, and my voltage goes back down there and starts to go up. And of course my current goes down. And then I flip the switches again. Now I'm pushing current back in. The magnetic field starts building again. And we just get this over and over again. And so I am now putting alternating current across it. And I showed that as I did this at lower frequencies, I got less average pushback from here. So I had less inductive reactance. But if I did it faster, I got more average pushback, increasing the inductive reactance. Well, I told you that just to tell you this. I want to make a little slight change in that. So here we go. I'm going to change this to a variable resistor instead of 2 switches. Now, if you didn't follow what I just talked about, you need to review my videos and reading material on inductors in DC circuits and in inductive reactance to make sure you thoroughly understand what I just explained. But now I'm going to change this to a variable resistor, and I'm going to make this oscillator by having an intelligence, maybe a little green man. Let's put him here, who's controlling that resistance, and his job is to make that resistance go up and down to get an oscillator here. But let's get rid of him for now. He's just in the way. Now, first make this a very low resistance, maybe on the order of 5 or 6 ohms. So now I am going to get a fairly large current that goes into the inductor. Let's draw our graph here again. Time, voltage, and again our current. And so high current's going to go in there. That magnetic field builds. We're going to get a high voltage across the inductor. It's going to be a consumer at this point, so current going in, we get a backup of voltage, higher voltage to lower voltage, and that magnetic field starts building very quickly and then slows down, so we get suddenly a very high voltage across the inductor. But as that magnetic field slows down, it's going to drop down, and of course what's going to happen to the current? The current is going to be going up like that. Now what I'm going to do is, instead of opening a switch, I'm going to suddenly increase that resistance, maybe up to 10,000 ohms, a very high resistance, maybe even more, but just a very high resistance. So I've essentially opened that switch. So this current suddenly drops down. I'm no longer pushing the same amount of current in there, so the magnetic field is no longer building and suddenly starts to collapse. So it's the same as me opening the other switch by simply making this a high resistance. Decreasing the current through there causes that to start to collapse. But of course the inductor wants to keep the current the same, so the current's not going to change much, but the voltage is going to suddenly what? That magnetic field starts to collapse, so now it's going to be pushing the current instead of blocking the current. The current's going to stay the same at this point, but it's, instead of being held at a certain current by the inductor, now the inductor is pushing it at the same rate. So the inductor is going to what? Become a current source. So it's going to be pushing current out the positive side and taking it in the negative side. So we get a voltage reversal. And then as time goes by, that magnetic field is going to collapse slower and slower, so that voltage differential is going to become less, and we're going to work our way up towards 0 volts. And of course the current is going to be dropping down proportionally. Now I'm going to take this very high resistance here and I'm going to crank it back down to a low resistance. So now the current is going to increase. I'm pushing it in now. So I'm pushing it in, I get a backup, so I get my higher voltage here, my lower voltage there, so my voltage across my inductor suddenly flips, goes back up there. And as time goes by, the magnetic field is building, but it slows down, so it's going to be pushing less and less. I get less and less voltage. And then, of course, the current is going to be increasing. And then when I get there, I'm going to suddenly crank that back up to a high resistance, causing the cycle to happen all over again. So I'm getting exactly the same thing, except now instead of having those two switches, I simply have a resistance. Low resistance, high resistance. Low resistance, high resistance. And so I get the same effect by simply changing the resistance here. So now we're just one step away from making our oscillator. We just need a component that's going to periodically change its resistance in, how about in response to the current? So the current goes up here, it changes its resistance to a high resistance. So the current tries to drop, the magnetic field tries to decrease, causing current to flow in the opposite direction, and then the current goes down. Then when it gets to this point, we change that back to a low resistance, causing current to flow in. The magnetic field flips because now it's blocking the current instead of pushing the current. And so our voltage flips across the inductor, and our current goes back up. And we get up here, we simply change that to a high resistance again. We just need somebody to flip that between a low and high resistance at the proper current points. And that's where the tunnel diode comes in. So let's quickly review the tunnel diode. You need to watch my video on tunnel diodes if you haven't already, but let's take a quick look at how the tunnel diode acts. So here is a voltage versus current graph. So we were looking at voltage over time. Now we're just looking at voltage compared to current. First of all, let's just imagine a regular resistor. So let's say I have a 1 ohm resistor. And so let's put voltage on the horizontal and current on the vertical. So let's say I put 1 volt across that 1 ohm. I'm going to get 1 amp. So that's going to put us right there on the graph. If I make that 2 volts, I'm going to get 2 amps. If I put 3 volts, let's get that out of the way, 3 volts, I'm going to get 3 amps. So I get a straight line. And if I reverse the polarity across the resistor, we're going to graph that as negative current. What's negative current? Just simply means it's going the opposite direction. If I continue my graph, if I go negative 1 volt, I'm going to get negative 1 amp. Put us right about there. If I go negative 2 volts, I'm going to get negative 2 amps. Right about there. So I get that straight line. Now if I increase my resistance, let's make this 10 ohms. Now if I go to negative 1 volt, I'm only going to get 1/10 of an amp, so I'm going to be way down here. And so if I increase the resistance, my line is going to lay down this way. So higher resistance is going to tilt my line clockwise. But if I make this 0.1 ohms, now everything's going to go up by a factor of 10. So 1 volt's going to give me 10 amps. Or negative 1 volt's going to give me negative 10 amps. So lower resistance does that to me. So that's how a resistor acts to voltage. Higher resistance lays our line down clockwise, lower resistance twists it up counterclockwise, but the most important thing is we get a straight line. So we need to be following that before we talk about the tunnel diode. So let's draw that same graph. Tunnel diode, voltage, current, positive voltage, positive current, negative voltage, negative current. And if we are reverse bias that diode, let's draw the diode symbol up here. There's our tunnel diode. If we reverse bias it, higher voltage to the anode, lower voltage to the cathode, we're going to be down in this region here, and it's going to act pretty much like a fairly low resistance, maybe on the order of maybe 5 or 6 ohms. And if we reverse that, now with a regular diode, we expect that to be a very, very high impedance at first, and we get a very, very low current, and then after a certain voltage, that's going to turn around and the impedance is going to drop and the current's going to go high. But that's not the way a tunnel diode acts. When we forward bias it, it still acts pretty much like a resistor for a while. So, looks pretty much like a resistor. However, when we get up to approximately 50 millivolts, depending on the particular diode, we're going to reach probably around 80 milliamps. And I'm looking at this particular graph. This is a real-world graph on a modified oscilloscope to show the actual curve of a particular tunnel diode. I don't know which one because I can't find that, but this particular tunnel diode acts this way. So back to here, at about 80 milliamps, as I increase my voltage, so let's go to 0.1 volts, there's 0.05 volts, 50 millivolts. What's going to happen is the tunnel diode, the little green man in the tunnel diode, has instructions to do whatever he has to do with the resistance. So let's draw that model real quickly over here. So here's our tunnel diode. Let's put a resistor here for good measure. And it's forward biased. And it looks a lot like the Zener diode, except it's forward biased instead of reverse biased, and it looks like a variable resistor. And we have in there our little green man controlling that resistance, and he's following a chart with instructions. You make that resistance whatever it takes to follow this particular curve that we are drawing here. So I will leave that there just for good measure. So at about 50 millivolts, his instructions are don't let the current go any higher. So as the voltage goes up, he's going to exponentially increase that resistance, forcing that current to heel over. And around here, we're going to be something like 250 ohms, where over here we were about 6 ohms. So our resistance is going to go up, and as we increase our voltage, the little green man is going to increase his resistance exponentially, so we get to about here, and he's increased it to about 1,000 ohms, and our current has gone down to maybe 40 milliamp. I may not have these numbers exactly right, but this is going to be pretty close. So if we double our voltage now, we're going to quadruple our resistance, and that's going to continue to right about 0.3 volts. So it's going to keep going down, and then we're going to reach about 0.3 volts. His instructions are, now you can let that current go up. So he's increasing his resistance exponentially to force the current down as the voltage goes up. But then he gets here and he's allowed to decrease his resistance and allow that current to go back up. And it's going to pretty much follow a diode curve, and this particular diode we looked at was a germanium tunnel diode, so it's going to have this point at about 0.3 volts. So nothing really mysterious there. We have a region here called negative resistance because as we increase our voltage, our current goes down. Well, what is that? It just means that the little green man is increasing his resistance exponentially as our voltage goes up to force the current down. So that's just what the tunnel diode does. It increases its impedance exponentially as the voltage goes up between about 50 millivolts and about 0.3 volts, causing this anomaly here that we call negative resistance, and it follows that curve. So there is the basic idea of the tunnel diode. I do have a more thorough video on it, which you should watch if you're not following this. But that's just what it does. Follows that curve because the little green man makes it follow that curve. And it's just a change in impedance, about 6 ohms, about 250 ohms, about 1,000 ohms, just increasing its resistance exponentially. And then here it changes the resistance to follow a typical diode curve. Now we are ready to look at a tunnel diode relaxation oscillator. So for simplicity, let's just use a battery at this point. In reality, we're going to have something like this. Here's a battery. We're going to have a voltage divider, and then come off of there to get our bias voltage. But just for simplicity, I'm going to make this a 0.15 volt battery at this point. So there it is. Positive to negative. And we're going to put our tunnel diode right here and an inductor here. Now here is a working circuit in a simulator at the website that I'm putting right here, fallstad.com. And I'll put the full link to this actual simulation in the description. Shows a working circuit with some working values in there. So back to our demonstration here. Let's see what's going to happen. Let's just put a switch here just for something to start things off. And before I do that, I want to put our curve for our inductor over here so we can follow that again. So here's what's going on over here. Remember, we had time along this axis, and we had voltage and, once again, current in blue on the vertical axis. And let's put our curve for the tunnel diode over here, just for the positive voltage part. So that tunnel diode is going to go up to a certain voltage, down, and then back up. That's going to happen at roughly 0.3 volts. And this is going to happen at roughly 0.05 volts. And our current here will be approximately 80 milliamps. So 0.3 volts. Let's make that about 0.4, and over here about 0.5. So this is milliamps, and that's volts. All right, here we go. Take a breath. Let's flip that switch and see what this is going to do. So we flip the switch, and at this point, what's that diode look like? We've just flipped the switch. We have 0 volts and 0 current. We're over in this region here. And what does it look like? It looks like about a 6 ohm resistor. So let's go ahead and get rid of our diode. Just see that as about a 6 ohm resistor. So this is going to do just what inductors and resistors and voltage sources do. So we're going to have a surge of current into that inductor. It's going to build that magnetic field. It's building very quickly. So at first it's going to cause a voltage that's positive to negative. Conventional current goes into the impedance. We get a backup of voltage, positive to negative, and it's going to be approximately equal to that, so 0.15 volts. So we have 0.15 volts pushing this way, 0.15 volts pushing that way, no current, so we are down at this point in the graph right there, no problem. Now as time goes by, what's going to happen? That magnetic field is going to continue to build, but it's going to slow down. So our high voltage is going to start to drop, and our current is going to go up. And when that current reaches approximately 80 milliamps, what's going to happen? So we reach about 80 milliamps. Remember what happened there? The little green man's instructions were don't let that current go up. So he increases his resistance exponentially as voltage goes up to prevent the current from going up. So what happens at that point is suddenly this becomes around 250 ohms, somewhere right around there. And that means that this current is going to attempt to stop because we don't have as much pushing it, but we have that magnetic field, and when the current attempts to stop, that magnetic field starts to collapse, which causes it to force the current to continue. What's the current going to be? It's going to be approximately 80 milliamps because it can't change instantly, so it's stuck right there. But what's going to happen? That magnetic field is collapsing. So now it's pushing current in this direction. What's going to happen to the polarity across this inductor? Well, now it's a current source, so conventional current comes out the positive side. So the voltage across the inductor suddenly flips. Let's go down and do that. Let's get that little T out of the way. So now we're at that point there. So what's going to happen along this curve here? Here's where you start getting some hand waving. I'm going to do that for just a second because I'll explain it in a little more detail later. But basically this is going to go up to about 250 ohms, but that current is going to try to continue to go down, so this is going to rapidly go up to 1,000 ohms, 2,000. It's basically going to go toward infinity, trying to block that current as the voltage goes up. So this is going to pretty much, oh, let's just throw 10,000 ohms here. I don't know what it's going to be. I'd have to do some experimenting and measure. It's suddenly going to go to a very high resistance, but the current's going to stay the same. So now we're at this point here. This has reverse polarity. The current has stayed about the same. This resistance has increased tremendously, and that magnetic field is going to start collapsing, and that means our voltage across the inductor is going to go down, 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 and our current is going to do about the same. And when that current gets down somewhere, let's not worry about exactly where yet, but somewhere, well, we're going to end up eventually getting to this point here. And so the tunnel diode is supposed to allow the current to go up, but the inductor is not going to allow that current to change. So the tunnel diode is going to start decreasing its resistance, trying to allow the current to go up as the voltage goes down. The inductor is not going to allow that, so this is going to suddenly drop to a very low resistance. Let's put it back at 6 ohms. So now we've dropped that down to 6 ohms, and like we did before, now our current's going to start pushing back in. What's going to happen? Now our current is pushing into the inductor. So now that voltage is going to reverse polarity. We just reverse polarity. It's going to start going down as that magnetic field slows down. And of course, what's our current going to do? It's going to be increasing. And then when it gets back to 80 milliamps, I guess we're back over here again. I'll explain that in a little more detail in a minute. It's going to switch to a high impedance again. That's going to slow down the current. Magnetic field is going to start to collapse. Again, that's going to change polarity, and everything is going to cycle over again. So in a slightly oversimplified view, that tunnel diode simply acts like a resistance that keeps changing. And because it changes at different currents, it changes at about 80 milliamps, then it changes at, oh, I don't know, let's just guess about 20 milliamps. So it becomes a high impedance at about 80 milliamps, but it doesn't go back to a low impedance until it gets down to about 40 milliamps. So we have some hysteresis there, which was required for relaxation oscillators. And so it goes back down, and then when it gets down to about maybe 20 milliamps, it suddenly switches back to a low impedance. And so now this starts going back through its increasing magnetic field cycle. And then when it gets to 80 milliamps, it suddenly switches back to a high impedance. And so we get that hysteresis. So in a nutshell, I've oversimplified how this works. So let's take a quick overview of that. At first, This is around 6 ohms. When the current gets to about 80 milliamps, that switches to a very high impedance, let's say 10,000 ohms. So the current starts to drop. When that gets down to about 20 milliamps, that switches back to a low impedance. So we have the switch going on, off, and it has that hysteresis. So it goes on at one current and goes off at a different current. And so we get that. So in a nutshell, that's what the tunnel diode does. But let's take a closer look to see why it does what it does. So let's go back over to here. Let's erase that and just look at it in just a little more detail. So once again, here is time, here is voltage and current. And we'll put our 80 milliamps, let's say right about there. So once again, we flip the switch, we get a surge of current into the inductor. Magnetic field is building very quickly, so we get a voltage across there saying, oh no, you're not going in there either. So we get a high voltage. Let's put us right there at the beginning, but very low current. Because why? Because this is approximately the same voltage as that. So this looks like a battery in reverse pushing the opposite direction. So we get no current. We've already gone over that. But as time goes by, this magnetic field is going to slow down. So the back EMF is going to decrease. So this voltage will go down. What will it go down to? Let's not worry about that, but it's going to go down. So less voltage there. Here's the voltage across the inductor dropping. And at the same time, our current is going up. And when that current reaches about 80 milliamps, what's going to happen? This resistor is going to jump up to some very high resistance. Let's just say 100K. Don't know what it is, but it's going to be very, very high. So this current tries to slow down. Now here's where some strange things appear to happen, but we'll see that they have to happen. So the current tries to drop. That means the magnetic field is going to try to collapse. So as that magnetic field tries to collapse, it's going to continue to push current in this direction. It now becomes a power source. So current is being pushed out the source, which will come out the positive side and back in the negative side. So our circulation is going to be that direction. So we have reversed polarity. So that is going to be represented by that going down to some voltage. What is it? Could be much higher than this. Probably will be. Because remember, it depends on how fast that magnetic field collapses on how big that voltage will be. So where are we over here? We're at the top of this curve over here at about 50 millivolts. So at this point, what's going to happen? This magnetic field is going to be collapsing. At first it collapses very fast, but it's going to slow down. So that voltage is going to decrease, but that means that the negative voltage is going to become higher. So the difference is going to become less. That voltage is going to come up to some higher voltage, and the current is going to try to decrease. But what's going to happen? The tunnel diode, as that current tries to decrease, it's going to increase its resistance exponentially to try to force it to stay high. What's going to happen over here? The coil is not going to allow that current to go down. So the tunnel diode, as the voltage goes up, it would like to just, increase its resistance and allow that current to go down. This will not allow the current to go down, so we're stuck. Let's do this in blue. We're stuck up here at approximately 80 millivolts. Cannot change rapidly. The little green man is increasing his resistance tremendously right here, trying to make that current go down. Okay, let's stop and take a look at what we've got going here, though. We have to look at some voltages. Let's just say, get rid of some of our clutter here. There's our current now flowing in that direction. And this is going to go to some negative voltage. Could be higher than that. Let's say this tries to go to 10 volts. Just a number I'm throwing out there. We'll figure out exactly what voltage it has to go to in a minute. So that tries to go to 10 volts. So now we put on our Kirchhoff's voltage law hats and start looking at what the voltages are going to do around this circuit. So here is the black probe of our voltmeter. So that's going to be our 0 volts. We are going to have plus 1.5 volts here. And what are we going to have right here? Well, we have 0 volts here, and we are going down in voltage now. Remember, this has to be 0 volts. Why? Because 0 volts is where you put the black probe of your voltmeter. That's by definition, that's where 0 is. Remember, 0 volts is not the absence of voltage, but just some voltage that we have designated as the point where we measure our voltage from with my imaginary black probe here. So the voltage here is going to be 10 volts lower. So that wants to be minus 10 volts. So that voltage is trying to shoot way, way up. The little green man in the tunnel diode is saying, oh, well, yeah, but your current has to go down. It's increasing its impedance tremendously, trying to force that current down, as this is trying to force the difference in voltage across here up. What's the difference? It's 11.5 volts. Minus 10 volts plus 1.5. We've got trying to get 11.5 volts across there. I'm just making that up, but it's a number. So what is going to happen? First of all, the current cannot change instantly because this inductor is pushing the current. So where did this happen? It happened at approximately 80 milliamps. So our current is going to have to stay right there. At the same time, our little green man is trying to increase his impedance because the voltage is going up. The little green man is increasing his impedance, trying to force the current to go down. So what's going to happen? Is there somewhere along this curve where he can settle his resistance in, where he can have some kind of voltage across here and yet have his current at 80 milliamps? And if we draw this across here, look at that. It's perfectly happy to be over here. And let's say that's at about 0.5 volts across there. So that means that this tunnel diode is going to be perfectly happy. Remember, this is our tunnel diode here. That tunnel diode is going to be perfectly happy if it can have, about 0.5 volts, positive to negative. So what voltage here would give us a total of 0.5 volts? Do that. Had my voltages wrong. It doesn't matter. Shoot. So I didn't have 11.5 volts. I had 10.15 volts. That doesn't change anything. So just everything's still doing the same. We're still trying to go someplace we can't go. This voltage is made up anyway. So we're still good. It's perfectly happy with 0.5 volts across it. So what voltage will we have? If we have positive 0.15 volts here, we're going to have negative 0.35 volts there. And that will have just the right amount of current flowing across here. That will cause the magnetic field to collapse at just the right rate to give us across there, let's do it in black, 0.35 volts. So if we follow Kirchhoff's voltage law, we have 0 volts here, we gain 0.15 volts to there, we lose 0.5 volts to here, giving us minus 0.35 volts, but then we make that up with this voltage source here, minus 0.35 volts plus 0.35 brings us around to 0 volts. So that satisfies Kirchhoff's voltage law. So our inductor is going to be forced by the nature of the laws and principles and all of the components that we have here to collapse its magnetic field at the right rate to give it 0.35 volts. It won't be able to collapse faster because the impedance of this tunnel diode is going to be just right to hold that current at just the right current, that it collapses at just the right rate. And so that is going to force us into this condition here. Once again, plus 0.15 volts. We lose half a volt. Now we're down to minus 0.35 volts. Now we're going to gain 0.35 volts to get to 0. So what goes on in here, I really can't say because it can't happen instantaneously. Nothing does. But this is going to settle its impedance to whatever it takes to make this circuit what it is. We can actually see what that resistance will be because we have half a volt across it. And we know this is going to be approximately 80 milliamps. So 80 milliamps and a half a volt is going to give us 625 ohms. So that's where we settle. The little green man adjusts the resistance of the tunnel diode until he finds himself over here at 0.5 volts. Now this is approximate, but it'll do. Finds himself here at 80 milliamps and at 0.5 volts, and he's perfectly happy to be there, and it takes 625 ohms to do it. And the circuit is perfectly balanced. So there's some of the hand waving goes on. Well, it has to jump from there to there. Why? Because it has to. Because that's where the tunnel diode is going to have to settle its impedance to satisfy the voltage and current that we must have at that particular point in time. So now what's going to happen? This magnetic field is now collapsing, and that means that the voltage across here is going to be getting less and less, which means as this voltage decreases, that means that this voltage is going to decrease. Its absolute voltage means it's going to get closer to zero. So it's minus 0.35 volts now. Let's just say it's going to drop down to minus 0.2. That's going to put a total of 0.35 volts. So it's gone from 0.5 down to 0.35. So now this has dropped down to where we're somewhere right around, I'll do it in red, to that point right there. Well, maybe a little closer to right there. So this tunnel diode is perfectly happy to let that voltage decrease and follow this curve. So he's changing his resistance. What is it? That doesn't matter. He's just watching the curve and cranking his variable resistor. We'll remind ourselves that that is a variable resistor being controlled by the little green man in the tunnel diode. So he's perfectly happy to adjust his resistance to whatever it takes to let the tunnel diode follow along that curve as that magnetic field collapses. And then what's going to happen when that gets down to right here? Now we've got another situation like we had before, basically like we have an irresistible force meeting the immovable object, whereas the voltage tries to go down, the current's going to try to go up. So the little green man is going to start decreasing his resistance exponentially to allow the current to go up. But what's the conductor going to do? It will not allow that current to change instantaneously. So right now we're down around what did we decide? Around 20 milliamps? Roughly. Doesn't really matter, just wherever that dip is. So now we're down there. And as that voltage tries to go down, the little green man is going to try to decrease his resistance to allow the current to go up, but it cannot go up. So we're stuck at this point here. So we're pretty much like we were here. He's trying to change his resistance. The current can't change. So where are we going to end up? Roughly over here. And that's going to put us once again at about 6 ohms. Because remember, any voltage around in this area, this is going to have 6 ohms of resistance or impedance. And so it's going to bring us back over there to where this is again about 6 ohms. Let's take all these numbers away because they're no longer relevant. And so now we are back to this point here. Our current has dropped down to about 20 milliamps. Our voltage has dropped down across here appropriately. This is suddenly going to go down to a very low resistance, causing the current to start flowing that way. Now it's being pushed this way. This no longer has the energy it had, and so it's going to suddenly reverse. So now instead of it creating current, current is going into it. It becomes a consumer again, so current is flowing into it. What's going to happen? It's now an impedance. So conventional current goes into the impedance. This becomes positive. That becomes negative. What's the voltage? We can follow it up here, but it doesn't really matter at this moment. This reverses voltage back up to there. And so now we're just simply starting the cycle over again. So as that magnetic field builds, it slows down, the voltage goes down, the current is going up. What's going to happen when it hits 80 milliamps? The irresistible force hits the immovable object again. It has to adjust its resistance to something that works, jumps back over to here again. And so what we find is that as this tunnel diode keeps adjusting its resistance, just following all these principles we've been learning for all this time, has to keep changing its impedance from about 6 ohms to about 600 ohms. then relaxes that, allowing this curve to happen. Then it has to jump back down to 6 ohms. So we get this hysteresis loop here. And that's what's in the simulation. You can see at the bottom, it's showing the hysteresis loop happening on the voltage versus current on the scale down below the circuit up higher. So that's why this particular type of tunnel diode oscillator does what it does. It's doing things we can't really fully understand, because why is it jumping from there to there? Well, it has to. We showed that it has to jump. And it's basically just that little green man in the tunnel diode that's changing his resistance to make sure he's somewhere on that curve. So he's on the curve here, jumps over to here because he has to, because the current can't change, but the current can now drop down, but now it can't go up, so he has to jump over here. So now he can go up, now he can go down, now he can go up, now he can go down, and we get that constant oscillation, which we can pick off here as our output, to where we see the voltage doing this, and the current doing that. And now we have a tunnel diode relaxation oscillator. Now we understand that one. Now we're going to show the next type of tunnel diode oscillator. And if you think this was complicated, oh well, let's see what we have coming up next. Let's erase these and redraw them if we need to. Okay, we're going to start out with our same voltage source. For convenience, we'll make it 0.15 volts. Go through our tunnel diode, through our inductor. Now we're going to put a capacitor in parallel with that. Now you'll see that these circuits always have a resistor in parallel with that, but we're going to ignore that because that simply changes the Q factor of the inductor and doesn't change the concept of how this works. Here's from that same website a simulation of this particular oscillator that we can look at. I'll link in the description below. But let's just go ahead and look at how this acts this time. So now the key is going to be what's going on over here, which is a tank circuit. And I didn't review that, but let's do that real quickly. What does a tank circuit do? Well, let's just draw one over here. We have an inductor in parallel with a capacitor. And if we put some energy across this, so if we put a battery across this and then remove it, the current is going to at first go through here and charge the capacitor and put a high magnetic field across this inductor. But when we take the energy off, we're going to find that whatever the current was doing at the time, it's going to continue. And so what's going to happen is that magnetic field is going to collapse as it charges the capacitor. Then we end up with no magnetic field and a charged capacitor, which is going to then push the current the opposite direction, charge the capacitor the opposite direction, and the magnetic field is going to build and collapse. And in a nutshell, we're going to get our energy going back and forth between the inductor and the capacitor. If we look at the voltage across it, we're going to see the voltage go up and down and up and down and up and down and dampen out as the energy is dissipated as heat in the resistance in the circuit. Okay, now, if we want an oscillator, we need to somehow keep that energy in the circuit. We don't want it to dampen out. How are we going to do that? Well, let's change this to a resistor. And make that a variable resistor. And now what we're going to do is have our little green man get in there, and he's got a job here. He's controlling that variable resistor, and his job is to watch this. Let's get that out of the way. To watch our oscillations as they dampen out. And what he wants to do is kick energy in and force this voltage upwards. So what he's going to do is, at just the right time, starting perhaps about here, he is going to decrease his resistance, causing more current to flow from the battery into the circuit. So let's back up a little bit. We have a switch here, and we switch the switch, take it off, get this going, but now we're going to close the switch so that the little green man has some energy over here to work with. And he is going to watch this, and he's going to decrease his impedance. As he sees the curve get to about here, as he decreases his impedance, what's going to happen? We're going to get more current. That current's going to hit an impedance, right? Which means we're going to get a voltage across it. That voltage Depending on the current, the more current, the higher that voltage is. So that means he's going to be feeding energy in at just the right time, and he's going to increase the voltage across here and push that back up. But he doesn't want to keep it there because he's pushing the voltage up. We want to allow the voltage to come down now. So he's going to push this up to a very high impedance so we don't have much current flowing in, so that we allow this to go down in voltage. But then when it starts to come up again, he's going to start decreasing his resistance, allowing current to go in and push that back up. And so all we need is something that's going to follow this and decrease the resistance at just the right time to push that voltage up, increase the resistance at just the right time to allow this voltage to go down. And then we have a nice little sine wave oscillator. Now enter in the tunnel diode again. So let's redraw our circuit over here. There's our tunnel diode, which we will change into a variable resistor momentarily. There's our inductor. There's our capacitor. This is going to be about 0.15 volts. Okay, remember this is a tank circuit, so it's naturally going to want to cycle. That's going to be forcing the circuit what it does. So this is going to provide the impetus to cause things to happen as we need them to. And this is going to simply be controlling the current at just the right times. So let's draw the tunnel diode curve over here. So we have that to follow. So we're going to go up to some voltage, back down, and do that. That's going to happen at about 0.3 volts. That's going to happen at about 0.05 volts or 50 millivolts. And that's going to happen at about 80 milliamps, although these numbers aren't going to be so important here. So we're going to turn this back into a variable resistor controlled by the little green man. Now all we need to do is follow the oscillations over here. So that's going to go up and down and up and down and up and down and try to dampen out. So all we need to do is somehow get this to go to a low impedance when this voltage is high, the voltage here. When the voltage here is at its highest, we want this to be a low impedance so that it feeds current in there, causing this voltage to increase even more. So we push current in. What happens when you push current into an impedance? You get voltage across it. More current, more voltage. So we're pushing current in, giving us more voltage, pushing that voltage up. And then when this voltage goes down, we want this to go to a high impedance, so it's no longer pushing current in there, allowing that to go down. Now, we have to follow this carefully because it's following Kirchhoff's voltage law and doing everything it should, but we have to remember which voltage is going up and which voltage is going down to make sure we understand what's happening. So here we go. Let's put us in this part of the cycle. The voltage is going up. So let's say we're getting up to the highest voltage over here. So this voltage is at its maximum. Let's say at that point, just for convenience, let's say that's at 0.1 volts, positive to negative, of course. So as that voltage went up to 0.1 volt, what must be the voltage here? It's 0.1 plus that voltage must add to 0.15. So the voltage across here is going to be 0.05 or 50 millivolts. So that puts us right about here at the peak of this curve. So that means that we're at the highest current point. We're going to get our greatest current at that point. So this is going to be whatever resistance it is, low resistance around 6 ohms or so, very low resistance, allowing a lot of current to flow into there, which is going to tend to push the voltage across here even higher. So it's going to be pushing that voltage up, keeping it up where we want it. Now what's going to happen? This circuit, being a tank circuit, is going to reverse its energy. The voltage is going to go down, and so now the tank circuit is dropping down here, and it's going to head for its lowest voltage. So as this voltage goes down, what's going to happen? This voltage is going to go up, so our voltage is going that way. What happens when the voltage increases across the tunnel diode? As the voltage increases, the resistance increases exponentially, so this is becoming a very high resistance. I'm going to estimate around 2,000 ohms could become higher. So our current going into the circuit is going to be minimum, so we are not going to be pushing current in, therefore are not going to be pushing that voltage up, and it will be allowed to go to the lowest voltage it wants to go to. We're not pushing that voltage up. But then what's going to happen? This is going to go back up here, so we're going to get up to our higher voltage here, so this voltage is going to go up and up and up. As this voltage goes up, what happens? This voltage must go down so that everything balances. So that's going to take us back down that way, taking us along this curve back up to that point there. So now we're at the voltage here that's going to give us our greatest current. So there's our high current again. That's going to push the voltage across the tank circuit up, giving this a little push to put it back up where we want it. But then as it goes down, what's going to happen? This voltage goes down. So our voltage goes down, down, down. As this voltage goes down, this voltage goes up. So that voltage is now going back up again, and it's bringing us back to the point down here where we have the least amount of current. So a little current in there, so it's allowing that to go down, and then it goes back up. Once again, as this voltage goes up, that voltage goes down, takes us back downward, takes us back to where our high current is. High current makes that voltage go higher, pushes that back up. So actually, the sine wave generator using the tank circuit here is even easier to analyze than the relaxation oscillator, because this is simply changing its impedance going up and down, following this curve such that when we are up here, its impedance is low, pushing more current in, forcing that to go up and keeping the energy in. But when it goes down, the impedance goes up, meaning less current going in, allowing this to drop back down. As it goes up, impedance goes down, more current in, pushes it up. As this drops down, the impedance goes up, meaning less current, allowing that to drop again. So basically the little green man is just watching that curve and saying, less resistance, more resistance, less resistance, more resistance. Or what happens with the current? More current, less current, more current, less current. So basically giving us some positive feedback with just the right amount of negative feedback to get that exactly where we want it. So in the relaxation oscillator, we find that the tunnel diode is first over in this region, jumps over to this region, drops down to there, jumps over to there. But in the sine wave oscillator, we find that it stays in the negative resistance region. So high resistance, low resistance, high resistance, low resistance, perfectly in sync to go high resistance, low resistance, high resistance, low resistance. High resistance means going to be high current, pushes this voltage up. Low current allows that to go down. And if you look at the voltage across one of these oscillators, you'll see it's a little asymmetrical, because we're not pushing this up, pushing that down, pushing that up, pushing that down. We're pushing that up, allowing that to go down, but we're still feeding some current into it, so it doesn't go down as far maybe as we'd like. But it just simply gives it an offset, so we get this nice sine wave oscillation. So that is how a sine wave tunnel diode oscillator works. So now that we have done that, let's just draw the basic circuits just to put them up here, and I'll put the ones that we can do in the simulator up also. So now here is your typical relaxation oscillator. We go through a couple of bias resistors. So this is going to be some voltage, but we use a voltage drop to put this at about 0.15 volts. That goes to our tunnel diode and then to an inductor. And it does what we explained before. If we add a capacitor to here, then this becomes a sine wave generator, and it acts like the sine wave generator did. So now that we've done that, let's just take a quick look at a couple of practical circuits. So we have here one practical relaxation oscillator, and we have here one practical circuit for a sine wave oscillator with components that you could try to build. So tunnel diode oscillators seem complicated at first, but with a little explanation become hopelessly confused. Well, not really. You saw that they do what they must do, and they're not really that complicated. So I hope you found this useful and informative, and if you did, please give me a thumbs up. It helps the channel and helps other people find these videos. And if you want to learn electronics technology and perhaps become a certified electronics technician, or just get a jump start in your studies in electrical engineering, you can go to vocademy.net and sign up and take my free course. And as always, a big thank you to my patrons at Patreon and my other donors. I could not make these videos and provide this free education without your support, so I can't thank you enough. So if you want to help me put these videos online and keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support, or go to support.vocademy.net and see other ways you can help me put these videos up. Again, a big thank you to my patrons and my other donors, and thanks to everyone for watching.